So this is the first two-body system here, simple Atwood's machine. This is 2 kilograms, 3 kilograms, so it's going to accelerate this way, so I guess I'll draw that on here. Acceleration's that way. That one's going to accelerate up. So force diagram for each mass we'll do first. M1 here. M1's got gravity. We'll say call it FG1, and it's got the tension pulling it up, FT. M2 has its gravity, which is bigger, and the same force of tension, which I guess I should have made that a little smaller. This one's accelerating up, this one's accelerating down. Now, key here is I always like to make the direction of the acceleration the positive direction, right? So for M2, down's going to be positive, M1 up's going to be positive. So we're going to have to keep that in mind when we do this next part here. Set up Newton's second law for well, this should be a capital N. Newton's second law equations for each mass. Make the positive direction of your y-axis the direction of the acceleration of the mass. All right, so we don't have to worry about x direction here. It's just vertical, so it's just y. So for mass 1, some of the forces in the y direction, 1 equals m1 times the acceleration of 1. So I'm going to make up positive here, so it's going to be the force of tension minus m1g, which I guess I'll just put in the 20 newtons right now, equals 2.0 kilograms times A. Acceleration of 1, I'm just going to call A. They both have the same magnitude, so I'm just going to put the A in there. And this is why I make the direction of the acceleration positive, so I can just leave A positive in both equations. So for mass 2, some of the forces in the y direction for mass 2 is mass 2 times the acceleration of block 2, which is also just going to be A. But now I'm making down the positive direction here. So my equation is going to be a little bit backwards, right? It's going to be down positive, so it's going to be 30 newtons, mg, right? 3 kilograms times g, mg, 30 newtons, minus the force of tension equals 3.0 kilograms times A. All right, A2 is also A, but it's, the direction of stuff is a little bit different. So I have two equations, two unknowns. I'm just going to solve one of them for ft and plug it into the other one. So I guess I'll solve this one for f of t. This seems more natural to me. So ft equals, I'm going to get rid of units here as well, equals 2a plus 20. So I brought the 20 over there. And I can take this and plug it in over here for ft. Right, ft here is the same on each, but watch out for that negative sign. 30 newtons minus 2a minus 20 equals 3a. I put the n in there, I should have done that. I dropped the units on the other thing, so I should have dropped the units on that as well. But anyway, we're solving for a now. We plugged in for ft, solve for a. So I'm going to bring this over here. So there'll be 5a on the right, and then 30 minus 20 is 10. All right, 30 minus 20 is 10. Divide both sides by 5. A is 2, and then meters per second squared. Now, I'm going to guess this is the right answer. One of the reasons I think I'm pretty confident is that it's got less than g, right? It's got to be something less than g. And if in my head the difference between these two sides is 1 kilogram, right? So I don't know. It seems that we'd only have 10 newtons of net force acting on 5 kilograms of mass, so I think that would work out. Anyways, using both Newton's second law equations to determine the acceleration of the system and the force of tension acting between the masses. Oh, I guess I should have read this a little more carefully. Part B just really wanted you to set up the 2 Newton's second law equations, not actually use them to solve. So I did part of C already here. So acceleration of the system, I did that right here by doing the algebra. Now the tension between the two masses, I just got to take that A we found and plug it back in here. So let me write that down. Equals 2A plus 20. A equals 2 meters per second squared. So now I can take that, put it in for A. That's the force of tension. Force of tension is 2 times 2 plus 20. So it's 24 newtons, right? So I did a little more work up here than I should have. I should have just stopped this one right here. Those are the 2 Newton second law equations, and then did the math down here, but it doesn't really matter. All right, I'll quick do number 6 here. Get these uploaded so you guys have these, and I'll finish up the rest of those solutions tomorrow. So here we go. Determine the acceleration of the system shown below in terms of big M, little m, and any fundamental constants. Friction is negligible. All right, so that's going to be big M, little m. All right. I'm going to make a force diagram for each one of them over here. Okay, so big M is going to have Fn, Fg, and Ft pulling on it, no friction. So that's big M, capital M. Lowercase m is going to have, I should probably make this a little bit clearer. Lowercase m is the hanging mass. It's going to have the same force of tension pulling it up, and it's going to have its force of gravity pulling down. Fg big M, Fg little m. Those are different. All right, so Newton's second law. So for big M, the x direction matters, and for little m, the y direction matters. But again, because they're coupled together, they're accelerating at the same magnitude, right? So this one's acceleration is to the right, this one's acceleration is down, right? So I can add those little acceleration vectors next to my drawings, and I can use those drawings to help us do Newton's second law. All right, so let's try to put this together here. We don't need to do anything with the y direction in number 6 here because there's no friction. So I'm just going to look at the x direction here. For big M, sum of the forces in the x direction equals big M times A. So it's just Ft equals big M times A. All right, the force of tension is the only force acting in the x direction causing the acceleration. There's that. And this one over here, sum of the forces in the y direction on this mass equals little m times A. I'm making down positive here because that's the direction it's accelerating in. Force of gravity on this little guy is little mg. Force of tension is negative now. All right, I'm saying down is positive. Down is positive, so it's force of gravity minus force of tension equals little m A. And again, I make down positive so I don't have to try to put a sign on the A. So again, you see we got 2 equations, 2 unknowns. We'll take that, plug it in for the force of tension over here, and do the work. We'll show it up here. So mg minus capital MA, we just put that in for the force of tension here, equals little m A. And then we got a group-like term, so bring this over here. So I'll have little mg equals little ma plus big MA. Factor out the a, so mg equals a times little m plus big M. Divide by little m plus big M. And there's our answer. That's going to cancel. A equals little mg divided by m plus big M. We could use the blob method for this as well. I don't like to do that initially. I like to just do it with variables or with individual masses, put them together. You never really need the blob method. You could always just do it using each force diagram and then finding this set of equations. The Bob method here, kind of a side note, the system's total mass is m plus little m, big M plus little m. And the force accelerating it is little mg. There's no resistive force, right? It's just the force of gravity on the little mass is accelerating all of the mass. So when you do F net equals ma or a equals F net over m, you get F net is just little mg divided by the total mass of the system, m plus m. So you get the same answer, a lot quicker. Not necessarily always a legal operation though. I guess I'll quick throw number 7 in here because it's pretty much the same. We're just going to add friction to it. So adding friction to it, we have to now do the sum of the forces in the y direction technically on big M here. So big M changes a little bit. Sum of the forces in the y equals 0. So Fn equals big mg is all that tells us there. Sum of forces in the x direction equals big M times A, and now we have to factor in friction. So Ft minus mu capital Mg. So I have to factor in friction now to our force diagram. Fn, Fg, I'm just doing this quick. So now this one has the force of friction acting on it, so we gotta factor that in. So what that does is it makes our force of tension now equal to big MA plus mu mg. We're using the same equation from mass 2 here, right? Same exact equation we're gonna take from the hanging mass. The hanging mass hasn't changed. So for little m, we're still just gonna do mg minus ft equals little ma, but that's what we're gonna put in for ft here. Kind of running out of space here. So we have little mg minus big ma minus mu mg equals little ma. Bring the big one over there, so we get little mg minus mu capital Mg equals ma plus capital Ma, and we get very similar answer here. This is getting kind of crazy here. We get a very similar answer. We get A equals mg minus mu times big Mg all over m plus big M. I do the same thing up here. I factor out the A, divide both sides by big M plus little m. And then the tension, you just put A back into this equation. So this is going to be pretty annoying. Mg, so take that A, plug it back into Ft, and then you get this down here, minus oops, I just put that in for the wrong thing. Whoops. Back up. I gotta put it in for A. And then, oh, this is a disaster. And then we'll white out needed. So Ft equals big M times Mg minus mu Mg over M plus M, and then that comes over to this side, plus mu big Mg. This is very ugly looking. We could factor an M out of this and so on. Not pretty though, not pretty at all. But we'll stop there. Great, the last part was all out of the frame for that last bit of the video. So, very messy here. We plugged in the acceleration up here for the A here, and I guess I could have done it here. and then solve for Ft. And there's probably some sort of simplification we could do there, but I don't really want to do it. That'll be it for now.